Boom. Pure maths people, induction. I do a little tiny video on induction, but we're going to do a big, massive video. I don't know how long this will take. I could get to see the time on how long this is going to take. But pure maths people, we're going to dance in induction today. You know, induction. Well, in this video, let's talk about what's going to happen in this video first. In this video, we'll talk about how it works, how induction works. I'll run you through the whole thing like that. Watch the entire video. Watch the entire video. And the second thing is we look at the common questions that's coming for your exams. So the common types of questions that induction could come. Induction is one of those things that is a lot for a little bit of reward. So really watch this video and take a little practice to get this out of the way. I think induction is one of the topics you want to get out of the way from the earliest. So that's why I started off with induction. Sum of series. Why did I write sum of series twice? These are the two question types that could come. Actually, it's five types that could come. The sum of series for the first one, yes, sigma notation, expanded notation. We'll talk about that more. But you know, you could get this series where you have the sigma notation and then you could actually expand it out. You need to know how to do it in both cases. You need to know how to use induction to prove. It's a type of proof to prove divisibility, inequalities, variable, exponent. That's where the exponent is the variable. And a question like that come recently. I pulled out the question in this video, so we'll have a look at that as well. So in the exams, Pure Maths Unit 1 keep, you know, you have 3 sections. Each section will get 2 questions. Each question is 25 marks. Induction is in the first question, and it comes most of the times, and it goes for like 6 to 8 marks. And since there's 150 marks in total, 6 by 25, and this is how to divide by 3, 50% of your final mark. Induction come like between 2 and 3% of your final grade is induction. So you might be saying, okay, that was enough of this video. Time to turn 2 and 3% of the final mark. No. As I said, it's a little bit of reward for a lot of work, but so is a lot of things in pure math. A lot of things in pure maths, and some of the concepts you'll meet in induction, you really need to catch the hang of it to survive the pure maths rule. So keep watching the video. Now is a good time to press like on the video because we don't have much pure maths students. We have a whole set of math students, but not much pure maths students. So that make me feel encouraged to do more of the pure maths videos. I have a private pure maths lesson, but we'll talk about that near the ending as well. What's next? So, all right, let me examine how it works. If you have 1 plus 2, that is 3. 1 plus 2 plus 3 is 6. 1 plus 2 plus 3 plus 4 is 10. Right? You see the pattern here, right? You see the pattern here. This is a series 1, 2. I hear a kind of knocking by it, creeping me out. Okay, whatever. So I was saying, this is a sequence. 1, 2, 3, and that could go on and on forever. And it's a series now because we add in the sequence, right? The sum of the sequence, 1, 2, 3, 4 as the sequence. So we added up and we gain a little pattern occurring here. What is the pattern? Is there a pattern there? Is there a pattern? So you need to ask yourself, like, could you come up with a formula to identify what this number is going to be? Actually, yes, there is. 1 plus 2 plus 3 plus 4 plus, and you go on to some unknown number, n. The last term is n. Then, to find the sum of all of that, is half of that last term, n, multiplied by n plus 1. Now, there are ways to prove this, beautiful ways, and I will show you one. For those who are not adventurous and don't want to see it, double tap ahead and go further along in the video, and I'll start to talk about how you use induction to prove this, which is the whole point of the video, right? Induction. But I feel like this how we could show this in one way is so beautiful. I just decided to pick it out for this video. For those who are adventurous and love maths, let me go forward. So this is the sum of the first n natural numbers. let's see how we could show how this formula comes to life. Well, we'll use this guy, Frederick Gauss. They call him Fred. Fred was a German dude, 18th century, boss of a mathematician, prince of mathematics or something like that. Used to call him. But let me talk about little Fred, primary school Fred. When Fred was in primary school, he used to get trouble, and his teacher decided to punish him. And how she punished him? She tell him, add all the numbers from 1 to 100. So that was his task. You just sit down there and add the numbers from 1 to 100. Well, him being the boss of a mathematician that he is, and probably used to watch Cohen Springer on YouTube too. So Fred took 30 seconds and figured out the answer. From adding up all the numbers, 1 plus 2 plus 3 plus 4. Now, you know, this is the same thing we was doing, 1 plus 2 plus 3 plus 4 going all the way up to 100. This man took 30 seconds, got the answer, and bring it back to the teacher. Now, what do you think was his method that he used to solve this? Can you think of a way to solve this? He got the answer. What was the method to solve this? By the way, the answer is 5050. What is the way to find this? Let me start to give you hints. So what he did was examine the first number and the last number. When we add that together, we get 101. That's a hint. All right, another hint. If we take the second number and the second to last number, 2 plus 99, we add that together. 2 plus 99 is 101. There's a next hint there that's supposed to crack it open for you there. It turns out that if we're going in a nice little series like this, here's the answer. There are pairs that will always add up to give me that 101. It's just to find out how much of those 101s we have. And since there are 100 numbers, there will be 50 pairs. So the answer is 101 times 50. And my boy just multiply 101 times 50, and you can clearly see that's going to be 5050. Now, how does this has nothing to do with induction, by the way. And if you're still watching this part of the video, that means we could really be doing this thing. Anyhow, so how does this prove? Remember, we're trying to show that this is tied to this formula. Maybe you've seen it already. If you've seen it already, here's a boss. Here's how. Let's go in algebra mode. 1 plus 2 plus 3 plus on and on. And we don't want to say a number, so we'll say n, which is like any number. Any. That's what we'll use for the number, right? And before n is n minus 1. Because if n was like 100, 100 minus 1 is 99, 100 minus 2 is 98, you understand? But n could be anything in this situation. Now we need to examine what the pairs will be. 1 and n is n plus 1. 2 and n minus 1 plus 2 is n plus 1 again. N plus 1 again. You all understand what's going to happen here? Remember when we did Fred primary school penance, it was 101 just repeating itself for a certain amount for 50 times? Well, it's just going to be n plus 1 repeating itself for how many times? It's not going to be for n times, it's going to be for half of n over 2 times. So the answer is n over 2 multiplied by the n plus 1, which is the same as half n by n plus 1. I tell her it's sweet. It's sweet. Look at that. It's just sweet. But this is not induction. Let me go into induction. Let me go into the induction. Alright, so the people who skipped the video, well, they should be coming back in with us here. Coming back into us here. We just examined how we could deduce this, but we want to prove this using the principle of mathematical induction. By the way, if I say magnetic induction anywhere throughout this video, I say that when I'm teaching this all the time. I don't know, I like physics, so I end up putting magnetic induction instead of mathematical induction. All right, so how we're going to prove this is some steps that I want you to familiarize yourself with. Pn, P1, Pk, Pk plus 1, prove Pk plus 1, conclude. 6 steps. Pn, P1, Pk, Pk plus 1, prove Pk plus 1, conclude. The very important steps are the four in the middle. This and this is basically statement. And the really important steps are these 3. And the most important step is this one. All right, I didn't really teach anything yet, and all right, let me go in. So, let's talk about what these steps are about, and then I'll explain it using an example, right? So, Pn is called the proposition step. P1, we'll call that the base case. Pk is where we assume some random thing. Pk plus 1 is the hypothesis. Proving Pk plus 1 is where we prove the hypothesis. And then we conclude with, I'll show you what we always conclude with, right? So as I said, this is the big boy here. But these 3 are the whole inductive steps that we're going to use. So, pure math student, I'm glad you're still here watching the video. Let's go forward. The first step, Pn. That's the first step, right? Pn. So, we're using the same example. We're going to prove that same thing. The first step, Pn, you're just going to write, let Pn be whatever it is you're trying to prove. Write it like this. You'll catch the hang of it just now, right? So 1, 2, 3 plus 4 plus ... meaning everything in between there plus n. This is what we're trying to prove. You know why we're doing this? We don't want to write this big long thing every single time. Remember, in maths when you say let y equal f of x, so you just write y all the time. Let Pn be equal to this big long thing. Boom. First step, very easy. Second step, P1. You want to prove the first instance. You want to prove the first case. You want to prove the first term in the series actually works. P1, so you're going to substitute for 1. The left-hand side is 1. If you watch here, the left-hand side, the first case is 1. You don't need to add it to anything. It's just 1. And we need to substitute n equal 1 there and see if it's going to work out to be 1 then. So, left-hand side is 1. Right-hand side, if we put 1 here and there to replace the n, we get half of 2, which is 1. So it does work when we let n equal 1, left-hand side equal right-hand side. Now notice how this working is. Everything in red, you'll always need to write. Pn is true for n equal 1, you'll always need to write this. Always start off with your Pn. The steps I'm showing you here are critical. If you're new to this, even if you're not that new to it, write it down. Gonna save your life. So P1, Pn is true for n. The things in red, you'll always write it down. It doesn't matter what happens here. The third step, Pk. This is where we're gonna just choose out a random thing for n. K, right? So K replaces the n here, and the n there. Because we're doing Pk, right? Where n is equal to k. So we want to assume that this is true. We are assuming that it doesn't matter whatever n is, n can be some random thing called k. This statement still remains true. That's the third step. Simple like that. So step 1 to 3 is just pure knowledge steps. You just repeat back these steps that I show you. Steps 4, 5 starts to get a little, that's where it gets problematic for students. So the fourth step, Pk plus 1, instead of putting k by the n, we are putting k plus 1. So this is, remember k was some random value of n. K plus 1 is 1 more than that random value of n, which is vital to what we're trying to do. And I'm going to explain the whole process. Hold on. Stay strong. Stay strong if you don't understand what's going on right now. Stay strong. At the end of the video, you might understand a little more. But in the middle of the video, there's some explanation coming. All right, so 1 plus 2 plus 3 plus k plus 1. Notice here, this is k plus 1 and k plus 2. How did that happen? Remember, it was I think it was n by n plus 1, but replacing n with k plus 1. So that's k plus 1 there, and k plus 1 going to replace this n plus 1 So k plus 1 plus 1, that's k plus 2. So that's how we get those two things there. Get accustomed to that kind of little plus 1 end up turning into 2. Sometimes it'll be 2 turn into... Get accustomed to them little... Your algebra and your indices game must be on point to survive this induction vibes. Alright, so we need to prove pk plus 1 is true. Remember, everything in red you'll always be writing. It doesn't matter whatever the problem is. For keep in your exam, you will be writing this. Alright? So in the fifth step, we want to prove pk plus 1 is true, so long as pk is true. Remember, we assumed that pk is true. So now we need to prove that pk plus 1 is true, given that pk is true, which is an assumption. So let's do that. So we started off with pk plus 1 is this, which we just do. But really and truly, pk plus 1, that's the sum of all the k. Let me show you what I mean. 1 plus 2 plus 3. Let's assume k was 3. Let's say that k was 3, right? So this is the add up this. This is pk. But if I want pk plus 1, I'll need to add on one more term. 1 plus 2 plus 3 plus this term here, which is 4, which is, we could also call that the k plus 1 term. K plus 1, in this case, 3 plus 1 is 4, the fourth term. And in this, since we deal with natural numbers, is actually 4 as well here. So, let me show you how this is going to kill off the question. pk plus the k plus 1 term is equal to, this part here was pk from before, plus that k plus 1 term. So, we just need to manipulate that algebra to come back to this, and if it is equal to that, we would have proven that the statement is true by mathematical induction. Hold strong, watch it out. So what I'm going to do here, I could expand this. I could expand everything and just fiddle around with it, and it'll get back to there. There are different ways to do it, but I am going to take a half out of this for reasons. So if I take a half out of that, it'll actually be a half by this, which is a half by this, and a half by that. I'll just change that to 2. A half of 2 is 1, so yes, this is actually equal to that. So why I did that is because now I can extract the k plus 1 with scant courtesy. I can factorize out k plus 1 out of that. And I think you've seen it happening there. You understand? I pulled out the k plus 1 out of that. So k plus 1 by k is that, and k plus 1 by 2 is that. So your algebra must be on. This part here does beat students who algebra wasn't that tops or indices. Certain ones, divisibility. When you're proving divisibility, your indices game must be on point, which is the same as this. So you finish, except you want to conclude nicely, right? Your sixth step. All right, so I just have to show you the conclusion step. QED here means quod erat demonstrandum, which is Latin for that which is to be demonstrated, or something like that. We just write this every time we prove something in maths and pure maths and stuff like that, right? So QED, quite easily done. You call it that. By the principle of mathematical induction, excuse me, I have the cold rice making this video. By the principle of mathematical induction, Pn is true when n is a natural number. Now, I would advise writing out principle of mathematical induction here, and instead of just putting Pn, put actually the whole 1 plus 2 plus 3, what we substituted for Pn in the beginning. Just to, be all proper and thing like that. But this is my video and I feel it to do this like this, so I do it like this. Yeah, so this here is a complete look at the question, and as I said before, this goes for like about 8 marks. So you wanna be quick on this, so to just rip through this question. They just fall out like an essay that you had in your back pocket. This is where practice comes in. In conquering induction, you need real practice, real practice. Some students might still be saying, sir, I don't really understand, and I would like to understand a little more of the concept that is going on here. Have no fear. I have a little more. I'll explain it using dominoes. This is the first domino. This is your P1. We are trying to prove that if we poke P1 like this with our finger, poke, it's going to fall down, plack. And you know the nice noise dominoes is make when it fall down. Anyhow, so if we poke P1, it will fall down. So we take out P1, put him there, poke him, back, he fall down. Beautiful. Anyhow, the aim of the whole thing is to prove that all of these are going to fall down. But unlike these dominoes, in maths, we can't check every single number. You can't check every single thing going on here till infinity. We don't have infinite time. So we can't check all. If these dominoes were infinite, we can't check to see if all fall down. So here's what we're going to do. We are going to take a random domino. That's our PK. Put him here. And we are going to assume that PK falls down. Then we are going to take the one right in front of PK. That's our PK plus 1. And put him right here. And what we are going to test is that if this one falls down and hits this one will fall down as well. You understand? So we are making a continuation. We are showing that the continuation works. We are showing that if this one falls down, the one after it will fall down. So if we poke this one, pokes, and it falls down, clitics, and it hit the next one, clitics, and this one falls down too, we have just proven that every single domino will fall. You know why? Because we proved that if one domino falls, any random domino falls, the one after it must fall. So if we show that the first one does fall, it means this one will fall, this one will fall, this one. We have done a domino effect. Induction is a domino effect. We are inducing. You get your vibes. That's why we use the word induction too. It's that kind of. That is what really playing off in this question in a way. So we use the principle of mathematical induction in lots of ways, and these are the 5 common ones that could pop up in your exam. 2, 3, 4, 5. Right, I did count correct. You see these 3 here? Those are the most popular. I don't think I've seen inequalities in the past paper. I need to double check. And I didn't really see this in the syllabus too. So I might just leave out that one. But this came in a kind of weird way. It came under some of series or some kind of thing like that. I have the question here. So to conclude this video, I will show you examples using this. Now, the example that I started with was an expanded notation. If you remember, it was 1 plus 2 plus 3. This is an example of a series in expanded notation, right? Plus n. This is expanded. The not expanded notation is when we use that beautiful sign, sigma. I'll show you. Prove that for all, by the way, this is the mathematical symbol for all. That means for all. This is the mathematical symbol for all. For all values of n that are natural numbers, n belongs to natural numbers here. Meaning 1, 2, 3, remember natural numbers is counting numbers, right? For all values of n natural numbers, show this. So this is interesting. Just to verify, let's see what I expanded. If we expand this, what will happen? 1, plug 1 in there, 2 by 1, so that's 7 is the first term. 2 by 1 is 2 plus 5, 7. And plug 2 in there, 9. Plug 3 in there. Well, alright, it's doing that kind of thing like this. Y'all catch that vibe? Now this is a series, this is a sequence. So because we're using sigma, it means we have to add. So it's like 7 plus 9 plus 11 plus 13 plus ... plus n. So this is like the expanded look of that. But we don't want to do the expanded. Anytime it's in sigma, you should dance because you don't need to write all them stand numbers and that plus thing. And remember, pure maths is about time too. All right, let's keep going. So the first thing we do, Pn, that's a proposition. You just let Pn be equal to this. You know, this is just the same thing, right? And I tell you, that step is just food. All right. The second step, also food. You're checking to see P1 works for both sides. Now, why am I allowing all of that to pop out there? We are substituting 1 into this side, 2 by 1, and we get this 7. We just do that. 2 by 1 plus 5. And we're substituting 1 on this side too, because that's the first term, right? 1, where n is 1. That's the last in the series there. 1 plus 6, 1 by 7. So it's 7 as well. It's 7 as well here. So the statement is true for P of 1. Now you should notice that unlike the last example, we had like a left-hand side to work out there. In the last example, it was just 1. 1 plus 2, so we just pull out the 1. In this example, we had to actually figure out what the first one was. These little things is coming important with practice. You'll understand the little quirks and stuff. All right, so the statement is true for P1. PK now. PK, pastor's kid. PK here means, what are you doing? Just assuming a random value. K. So K is replacing the N. Now, a common mistake I see students making is replacing the R with K here in these kind of questions. Leave the R alone. The R ain't doing nobody nothing. The R is just our counter. We're just going when R is 1, R is 2, R is 3. K is the final value. That's where we're stopping at. So K is the important thing. So the N here is what we're really concerned about. That's it. Assume PK is true. So let's talk about PK plus 1. So I guess we're going to do the same thing. K plus 1 there, K plus 1 there, K plus 1 there. Already seen the K plus 1 plus 6. Remember I tell you, that thing is always happening. Alright, so K plus 1 plus 6. So we can see that this is going to be K plus 1 by K plus 7. Good. Now, every time you write PK, right, assume PK is true at the end. Every time you write PK plus 1, you say, let's prove PK plus 1 is true, or we shall show that PK plus 1 is true, given that PK is true, or something like that. Just make sure you have one thing that you do all the time. Don't forget it. Boom. The PK plus 1, when you're doing the sum, sigma notation, I like to start off with what was given before, or at least have that, when you're doing your question in chronological order, you'll have that there. So we need to find this whole induction thing. You're always trying to tie in the K plus 1 with a little piece of information from the K, right? So whether it's P or S, sometimes just put SK plus SK, SN instead of P, things like that to tie up. But you're always trying to take that K plus 1, that fourth step. That's the fourth step, right? 1, 2, 3, 4. You're always trying to take this fourth step and tie it into the third step, and that's like your fifth step. So you see how we start off here, showing what the K plus 1 is. I want to add in the K plus 1 term with the key. Let me show you what I mean. PK plus K plus 1, and by K plus 1 here, I mean the K plus 1 term. That term that comes after the K. PK plus K plus 1. Remember what PK is? PK is this. We just showed that. We just showed that here. PK is that. Why that green line still there? You know that green line affected me. Let me take that out. Out. Right. So we added in the K plus 1 term. It's going to go here. Some people just put K plus 1 here. There's a problem. Like last time it would have worked. But the K plus 1 actually has to go in there. That's the K plus 1 term. Because this is when R is equal to K plus 1. You understand what I mean? So K plus 1 is 2 by K plus 1 plus 5. Don't get that. Now we need to ask yourself, what are we really trying to do here, boy? Or we're really trying to simmer this down using our expert algebraic skills and make it look like that. So I think the best thing you can do here is expand those brackets. K by K squared. You're going to end up with a quadratic, and hopefully the quadratic factorized to give me those two binomials there. So K squared plus 6K plus 2K plus 2. Verify that. Verify that you get this quadratic here. That factorizes the K plus 1 and K plus 7 QED. Then you hit them your last step. This last step here, number 6, is always be the sweetest step to write, collect the marks. This is one of those self-correcting questions. you would always know whether you get it correct or not. Because it's not like you're trying to find a number. You're trying to prove something. So you'll always know whether, and you must take advantage of questions like these. So the two examples we did before, series, right? Expanded, sigma. Let's look at an example where we're showing if something could be divided by some divisibility. If it's divisible by. Prove that 6n minus 1 is divisible by 5 for all values of n positive integers, natural numbers. You know, they could say anything. By the way, this is a past paper question. This came very recently, 2016 or something like that. So we want to show that 5 will always divide this, doesn't matter what n is. Okay. All right, so we're always going to use the same steps that I said from before. All right, so let Pn, now this is some weird notation here. Let me just explain this. This magical line here is an accepted way to say that 5 is a factor of 6 to the power of n minus 1. It's actually saying that whatever is on this side is exactly divisible by there. So like I could write this. This is true. You understand? This is false because it's not exactly divisible by there. You don't need to make the line nice and dark like that. So I'm just using that because it's more convenient. Some textbooks will have, you write 6n minus 1 is you'll always have to write is divisible by 5. That's kind of take up time, and this is about time. You could go ahead and just use this little symbol here. Nobody will exit you for that. That's supposed to be understood. All right, so P1 is the statement saying that 5 could go into the 6. Pn is the statement, and P1 is checking for the base value. For the 1, we're going to put 1 there. 6 to the power of 1 is 6. Take away 1 is 5. This cold really affected me here. I hope I could make it out to the end of the video. All right. So this actually works out to be 5 on both sides. 5 into 5 is 1, so this is true. Statement is true. P1 is true. Statement is true for n is equal to 1, wherever you want to write. Pk now. We are assuming some random value of k. Now this little part here is where the magic happening, so pay attention. Saying that 5 could go into this one. Change the n to k, because we're using pk. Remember, we're pulling on the random value. But I want to write that is, or I will use this arrow sometimes. The 6k minus 1 is equal to 5 by a. This is important for algebraic purposes to solve the question, right? The a here is any natural number, meaning we're assuming that this is true, that 6k minus 1 will always have a factor of 5. 5 by some number. So I could always pull out 5 out of it, and there'll be some number a. You understand? So assume pk is true. That's that. Let's do pk plus 1. Pk plus 1. Pk plus 1. I put the k plus 1 there. And I'll have the same thing to set up, but I can't use the a again. So I'm going to use b. I'm going to use b. See, I use b. Some people will use m and p. Some people will use different. It's just a constant. It's just a natural number that this must be, right? Did I put 6 here? There should be 5. Boom. Because remember, we're saying 5 could go into this one as well. We're saying that if this is true, this must be true. We need to prove that. I'm going to finish that right there. We need to prove pk plus 1 is true. Take some time and just watch over the statement. Maybe you need to write it over just to get familiar with the algebra involved. We just basically replace the n with k plus 1 here. I could put a colon there to just neaten up that. We just replace the n with k plus 1 in this case. We replace the n with k there. And we are assuming that this one is 5b, this one is 5 by a. Now let me show you how you tie the two together and actually prove that this does work using mathematical induction. Remember this? this was the first four steps here. The fifth step is where the magic happens, where you need to tie the pk plus 1 with an inductive kind of step, a sleight of hand with the pk. So let's see how we'll do that for divisibility. Now, indices game must be on point for this. I remember, your indices must be out there, otherwise you won't understand what's happening here. Okay, there are two ways you could do this. There are more than two ways you could do this, but I'll show you the two ways that are most common for doing this. 6k minus 1, so we're starting off with the 6k plus 1, we're starting off with the k plus 1. We're not saying that properly tonight. 6k plus 1 minus 1. This is the same as, let's substitute out this negative 1. So that's one way we could go. Eradicate this negative 1 using information from what we had before. This. If I make negative 1 the subject of the formula here in pk, this 6k is going to come across here. Take away 6k, you understand? Take away 6k. So I can use that as a form of induction with the k plus 1 with the k. Watch it. 6k plus 1 minus 1. Remember, the minus 1 is really this. And we get this from, oh, look, I write it here in purple. Since negative 1 is actually that from your knowledge with the pk. And all that's left for you to do now is to simmer this down like Baji using some indices. 6k plus 1 is actually, remember, this is, if you have 6 of a plus b, this is actually 6a by 6b. Indices, right? Laws of indices. That's one way you could think of it. 6k plus 1 is actually 6k by 6 by 1 minus 6k. I'm just rearranging, bringing that k there, bring the 5a there. Pull out the 6k, factorize out the 6k from these two terms here. And that'll leave me 6k and 6 minus 1 here. The reason I'm doing this is because I want the 6 takeaway 1 to happen. And I'll get the 5 there. You'll catch the hang of it if you do a lot of questions. So you may understand this, but the reasons behind it will only happen when you start to practice questions and follow and figure out the whole SEPI. Alright, so 5, and 5 is there, which is this. That's basically proven right there, because we have two factors of 5 taking place. I can just make it neater by pulling out the 5 itself. See, I did that there. 5 by 6k plus a is obvious now that the 6k plus a must be the b from before, when we are assuming this 5 by b. So b is just some number, some natural number. It's proven here. Why? Because we have a factor 5 coming out as well of the 6k plus 1. Let's look at the other way. So if you like this way, you can use this way, free up yourself. And obviously after this, you state your conclusion. Let's look at the other way. We can say the 6k plus 1 minus 1, and we could start off one time. We don't induce anything yet. We don't pull in anything yet. We don't substitute anything yet. 6k plus 1. This is the same as 6 by 1 multiplied by 6k. Sweet. And this part here is a little more intuitive, a little less intuitive, in that you need to see that you want to split this 6 into 5 plus 1. And you'll see why we're doing that, because we want that factor 5 now. So you split that into 5 plus 1. This 6, remember, if it's divisible by 5, we'll split like what number we have into 5 plus the 1. 5 plus 1, when you multiply that out, we'll get 5 by 6k plus 1 by 6k. 6 to the power of k. When I say 6k, I mean 6 to the power of k, right? Plus 1, and don't forget the subtract here. Now, if you remember, this is very familiar. 6k take away 1. Let me just go back so you can see it. 6k take away 1 is actually the 5a. So I could scoot in my 5a right there. Come on, 5a. Where are we? We are about here. So this 6k minus 1, 6k subtract 1, we are going to just replace that with 5a. And we are about at the same spot we were last time. We pull out the 5. This must be equal to b. It's proven where b is equal to 6k plus e. So we always trying to squeeze out a factor of 5 out of the 6k plus 1, subtract 1 here, or whatever it is, depending on what they're trying to make you. It might be divisible by 7 in your exam, 8 in your exam, whatever they bring in your exam, you'll be prepared for. You just need to know along which area here you're going to push in your a piece of algebra from PK. That's the trick. That's the whole trick to solving this question. I think I have time to just do one more question. This video is already going crazy long. For all, this was the conclusion from before. For all values of n being natural numbers, this is divisible by 5 by the principle of mathematical induction. Okay, so this is another past paper question here. The trick in this one, and this one gives people problems, is that n up in the variable, boy. Up in the exponent. So this could be crazy. Now you notice they're using s instead of p, not a problem. They told us what s of n is. 5 plus 5 squared plus 5 cubed plus 5 to the power of 4 plus 5 all the way up to 5 to the power of n, and the n up in the exponent, up in the ceiling there. And now there's another trick here. There's 4. So this one was deadly, because this is going to play off when we reach to the pk plus 1. This 4, remember that 4 there. This is 4 times the sum is equal to this. So you need to show that by principle of mathematical induction. Let me dive right in. So you want to let p of n be equal to that. 3 marks. P1, check the left hand side. P1, left hand side. Left hand side is not 5, eh? Left hand side is actually 4 by 5. A 4 started to get trouble already. 4 by 5, because remember it's 4 times the sum. So this is the first term, yes, but it's actually 4 by the sum. So left hand side is 4 by 5. Right hand side, substitute 1 there. Both of them turn out to be 20. Left hand side equal right hand side. Anyway, you already pick up 1 or 2 marks there. Chugging along. Let's keep going. P1 is true. Next up is pk. So we're going to replace the n with k. It was n plus 1, so now it's k plus 1. We need to assume that is true. pk plus 1, replace the n with k plus 1. Remember, since this is already n plus 1, when you put k plus 1, it'll end up being k plus 2 now. And we need to prove that pk plus 1 is true. We need to prove that this is true. Let's see how we're going to do that now. Alright, so I already have some things here on the screen. You could take a look at it and see if you could figure out what's happening here. We have 4 by... This was pulled from before. The k plus 1, right? So we're starting off with this as our... What is it called that way? Reference. And we are replacing this now with the k, s of k. I hope I didn't say p anytime. S of k, 4 s of k plus, and then I put this 4 here because this is the big problem. 4, that was problematic for students. 4 by the k plus 1 term. Normally people know to add in the sk plus the k plus 1 term. But because they put this ridiculous 4 here, you want to put 4 by the k plus 1 term there. So it's going to be, and you could take some time and try and figure out the rest of the question now if you're feeling confident about it. It's going to be what we had for s of k plus 4 by the k plus 1 term. Now, remember how the terms work is like 5 to the power of n. So the k plus 1 term would be 5 to the power of k plus 1. K plus 1, but then you need to multiply it by 4 to get that left-hand side properly in that k plus 1 term. Alright, so 4 times the k plus 1 term here, so 5 to the power of k plus 1. I have 5 to the power of k plus 1 plus 4 by 5 to the power of k. This is like I have 1 mango plus 4 mangoes. So in all, I have 5 mangoes. Ha ha ha. Take away 5. They wasn't ready for we day. They wasn't ready for we day. And now, them blue lines are stay there. So you just do some algebra and pull him down so that he'll be equal to this. You always have a little reference there so you could see it. Let me just explain what's happening here. This is really 5 to the power of 1. And since they are being multiplied and they have the same base indices, laws of indices are going to come off big here. This is actually k plus 1 plus 1 plus 1. You understand? 1 plus that. So it turns out to be k plus 2, which is the same as what we said it should be. So since we worked it out and it's what it should be, it means this would work. So it's QED for this one too. Quod erat demonstrandum. What is to be demonstrated has been demonstrated. Boom. So hence PK plus 1 is true. We good to go there. Alright, so this is the number. You need to WhatsApp if you want to get smart, if you want to do more pure maths, or if you want to join the pure maths class. We do 2 hours every week. Working with some really top students from all around the Caribbean. If you want to join that class, join the WhatsApp group. Get into our Google Classroom. I'll be getting more tutors as well to work along with us. Coming down there, exam season. That group is going to be the best group forever that you would want to be in. So feel free to WhatsApp this number. It's $200 TT a month. Join up if you're interested in more pure maths videos. Let me know what topic is giving you problems. If you're interested in pure maths videos like this one. These pure maths videos are kind of long and take some time to make, right? So let me know which ones you're interested in. Make sure you press like on the video. Make sure you get all your pure maths students to watch it and things, so I'll feel encouraged to make more pure maths videos. Normally when I make a maths video, after some time it will reach 10,000, going up the road 20,000 views. But pure maths videos, not much students, right? So I need to watch the video, brother. Alright. If you haven't subscribed to this channel. I do lots of different subjects. I plan on doing some physics and chemistry. Yes, A-level people, I plan on doing some stuff for you. Some more advanced stuff as well will be starting to pop up on the channel. But I'll still be doing my bread and butter, which is mathematics for the lower level CSEC. And other subjects as well for CSEC. Blessings. I don't know why the screen gets so fuzzy.